in LJ Institute of Engineering and Technology in Department of Electronics and Communication. This video is about subject fiber optic communication. So friends, in this video, you will learn about the chapter number 5, power launching and coupling. So power launching and coupling. Specifically, source to fiber power launching. How to launch the power from the source to the fiber and the lensing scenes. So now, the source to fiber power launching. Now, very first, what is the coupling efficiency? So how can we couple the power? And from there, we can find out the coupling efficiency. So it is the power coupled into the fiber and to the power emitted from the source. So power coupled into the fiber, that is suppose the PE, PF, and power emitted from the source, that we will write at the PC. So PF theta is equal to PF upon PC. That is the coupling efficiency. So here in the diagram you can see that there is a source and there is an optical fiber. The power from the source, that is the PF, and the power emitted from the source, that is suppose the PC. So now we can write the equation that is for the coupling efficiency. Eta, it is the PF upon PC. Now, how to couple the power from the source to the fiber? So, source to fiber power launching. So, optical output of a luminescent source is usually measured by its radiance B at a given diode current, and this can be the radiance. So what is the radiance? It is the optical power radiated into a unit solid angle per unit emitting surface area. It is generally specified in terms of watts per square centimeter per steradian. So this is the unit of the radiance. Now the radiance is equal to power per unit solid angle multiplied by power per unit emitting surface area. So this is about the radiance. Now what is the solid angle? The solid angle, that is the projected area of a surface patch onto a unit sphere of a point. So now we can see over here that particularly the area, that you can see that the sphere, and how the projected area of a surface patch, onto a unit sphere of a point. So that particular angle we will refer to as a solid angle. Again in this diagram, it is given like this. There is a unit sphere, is you can see the surface patch from the center point of the sphere to the surface, and that space, that is the dA that you can see. So the angle which can be seen from the center of the sphere, that includes the given area on the surface of the sphere, and the value of this solid angle, that is numerically equal to the size of that area divided by the square of the radius of the sphere. So this can be used, for calculating it. Now the radiance, which is like the brightness of the source. Here you can see this graph in which the emitting area of the LED which can be shown, and there is a center of the emitting area. Now here, which makes the coordinate system, the spherical coordinate system, the r, theta and the phi, that we can see. So it is the radiance of the particular source, where that the V is the optical power radiated from a unit area of the source into a unit solid angle. Unit is the watt per square centimeter per steradian. So that is the unit of the radiance. Now, the source radiation pattern of a source that helps to determine the power accepting capability of the fiber. I mean, how much power that can be accepted by the fiber. A solid-based emitting LED that have a Lambartian output pattern. So, this pattern, okay, it is the emission pattern of the Lambartian output for the surface emitting LED. So, here the optical source is there, and at the various angle, you can see that the output pattern that can be drawn by using the equation B of theta phi is equal to B0 cos theta. This is my equation number 2. So it is the Lambartian pattern of the particular LED. And the H emitting LED and the laser diode radiation pattern can be found using this equation. It is 1 upon B theta comma phi is equal to sin square phi upon B0 cos B theta plus cos square phi upon B0 cos L theta, where T and L are the transverse and the lateral power distribution coefficient, which can be our the next equation. For the H emitting LEDs, L is equal to 1, and for a lesser diode that has the lateral, which is theta phi is equal to 0 degree, and the half power beamwidth of 2 theta, that is equal to the 10 degree. So by considering, by taking these values, we can find out this equation by putting the value in the previous equation. It is P of theta is equal to 5 degree, phi is equal to 0 degree. This value is the B0 cos raised to L 5 degree. It is equal to 1 half B0. So this way we can find out the emission as well as the radiation pattern. So therefore, the L is equal to log 0.5 upon log cos phi degree. It is equal to 180. Okay. So now the 182. Okay, that is the answer for C. Now the power coupled from the source to the fiber. So to calculate the power coupling into the fiber, consider an optical launch into the fiber. Now which is shown in the figure. So now this is the power coupled from the source to the fiber. So here as you can see that the optical source strip is there, the active area you can see, and there is a pattern. So out of that, onto that the fiber that is also drawn, the core and the cladding is there. Okay, so now what is that? That maximum power from the core, okay, and that we can see. So source radiation pattern, okay, and you can see that what it is our the fiber acceptance angle, okay, and whatever the power, okay, that goes out of the cladding, okay, that is what it's a loss of the power. So this way, how the power that can be coupled from the source to the fiber, that we have seen. So brightness of the source which can be expressed as B in bracket AS comma sigma S, where AS is the area of the source and sigma S that is the solid emission angle of the source, and the coupled power P that can be calculated as. So it is the PF is equal to integration of AF dAs sigma F B comma AS comma sigma S d omega S. So again we can write in terms of the r theta and the phi. So this equation that is the integration 0 to Rm, integration 0 to 2 pi, integration 0 to 2 pi, integration theta 0 maximum, b theta 0 theta comma phi sin theta d phi, okay, and bracket complete d theta as r into dr, where the Rm value that is equal to a, while Rs is greater than a, and it is equal to Rs, while Rs that is equal to less than A. So this equation that is about it. Now the next equation. Power coupled from the LED to the fiber. While the power is coupled from LED to fiber. Here we are considering the various situations, and based on the various situations, there are the various equations to solve or to calculate the power value. So while the power coupled from the LED to the fiber, so it is integration 0 to s, integration 0 to pi, then 2 pi b0, integration 0 to theta 0 maximum cos theta sin theta d theta and d theta s into r dr. It is equal to pi b0, integration 0 to rs, integration 0 to 2 pi sin square theta 0 maximum d theta s into r dr. It is equal to pi b0 integration 0 to rs, 0 to 2 pi and a square theta d theta s into r dr. So this is the equation for the power coupled from the LED to the fiber. So the final equation is P LED for the step index fiber is pi square rs square b0 na whole square. It is equal to 2 pi square rs square b0 n1 square into lambda. So this is for the power coupling from LED to the step index fiber. The total optical power from the LED, which can be defined as P of S is equal to AS, integration 0 to 2 pi, 0 to 2 pi by 2, b theta comma phi, sin theta, d theta and d phi. Again this equation that can be the PS is equal to pi rs square 2 pi b0, integration 0 to pi by 2 cos theta sin theta d theta is equal to pi square rs square into b0. So various situations and the various calculations that we have seen, and it is the final equation to solve the example, that is the P of LED for the step index fiber. It is equal to the PS na square if r is less than or equal to a, and this is the a upon rs whole square ps into na square if rs greater than equal to a. Now the graded index fiber. If the power coupling from the LED to the graded index fiber, then the power coupled from the LED to the graded index fiber, which is given as the power P of LED graded index GIN is equal to 2 pi square B0 integration 0 to Rs n square of R minus n2 square R dr, nr is equal to Na of 0 integration 1 minus R upon alpha whole raised to alpha, R upon A whole raised to alpha is equal to 2 ps n1 square delta in bracket 1 minus 2 upon alpha plus 2 whole raised to rs upon alpha, rs upon A whole raised to alpha. So if the medium between the source and the fiber is different from the core material with a refractive index n, the power coupled into the fiber will be reduced by the factor R, which is known as the n1 minus n upon n1 plus n whole square. It can be also important to solve the examples. So optical power that only depends on the radiance and not on the wavelength of the mode. So for a graded index fiber, number of mode that is related to the wavelength as capital N is equal to alpha upon alpha plus 2 pi a n 1 upon lambda whole square into delta. So this way we can calculate it. So twice as many mode propagates for the 900 nanometer as compared to 1300 nanometer. But the radiated power per mole from a source is Ps upon m is equal to V0 lambda square. Now, the power launching versus the wavelength. What is this relation? So, twice as much the power is launched per mole for 1300 nanometer as compared to the 900 nanometer. Now, we will solve the example based on this. So, for a surface emitting LED has a radiance B, that is 150 watt per centimeter square steradian, and radius of emitting area is 35 micrometer. Calculate the optical power coupled to the fiber with first is A1 is equal to 25 micrometer and Na is equal to 0.20 step index fiber. In second case, A2 is equal to 50 micrometer and Na is equal to 0.20 step index. So we will solve the 1 and 2 separately. So here the data are given to us, that are the P0 is equal to 150 watt per centimeter square steradian, RS is equal to 35 micrometer. Okay, so it is the 35 into 10 raised to minus 6 centimeter. Fine. And A1 is equal to 25 micrometer, Na is a 0.20 step index, and A2 is equal to 50 micrometer, and Na is equal to 0.20 step index. So now, for the RS greater than A1, we know the formula. The power coupled to the fiber, it is the P LED comma step is equal to A upon RS whole square PS into Na square. Again we will write the equation by putting the PS value in this. So it is the A upon RS whole square into pi square RS square P0 into Na square. Now we have the value of this A, we have the value of the RS, we have the value of the V0 and A. Putting all the values inside the equation, we can have the answer. It is the 370 microwatt. Now the second part. Now in the second part, you can see that okay, for the RS less than A2, the power coupled to the fiber that is given by P LED comma step is equal to pi square RS square B0 into Na square. Now put the value or the data given to us, and based on that we can have the answer. It is 725.41 microwatt. So this is regarding the equations while power coupled from the source to LED, LED to source to the step index fiber, gradient index fiber. Remembering all the equations, we can solve the variety of the examples like this. So it is regarding the the basics of power launching and coupling. So thank you very much everyone.